So you've been looking at some properties of gas laws. We just want to talk about some of the variables that we're going to be working with. Say you have, talking about air pressure. You did a little simulation where you had pressure sensors and you put them under the water, and when you put them farther down under the water, there was more pressure. And you know that from a swimming pool, when you're on the bottom, you feel the pressure more. Same is true for air pressure. Say this person is at 0 feet altitude, so say he's at the beach. When you're at the beach, you're at sea level. As you go higher and higher up, if you're in the top of a mountain peak, you're at a higher altitude. Bok Tower is about 100 feet above sea level, so it's a little higher. So this person at sea level, here's the top of the atmosphere, and there's this pressure, this air pressure pushing down. That column of air that from the top of the atmosphere down to their head is pushing down on them. And normal air pressure is 14 pounds per square inch. So every square inch on that person's head, you're feeling another 14 pounds of pressure pushing down. We don't notice that because we were born that way. We don't know any different. But if you're at the top of a mountain range, here's this little guy, he's not going to feel as much pressure because there's less air above him. So the higher up you go, the less air pressure, the less that big column of air is. If it's a balloon, the helium particles, as you saw in some of those simulations, gas particles bounce all over the place. They're bouncing around, they're hitting the inside of the container and bouncing off. So it stays inflated because those helium molecules, or the atoms, are pushing out. You also, though, have some air pressure pushing in on that balloon. So for the balloon to stay inflated, the helium has to be, the pressure of the helium pushing out has to be a little bit higher than the air pressure pushing in. And so then the balloon would stay inflated. If you had something like an oxygen tank at a hospital, there are steel containers, those are pushing out. There isn't really an air pressure pushing back in on that because it's a steel container. It's not a flexible container like a balloon. But anything that can give and take and move in and out like a balloon, we have to look at both pressures. Here's some marshmallow peeps you see around Easter time, some little bunnies and chicks. And so marshmallow is made of sugar and some air bubbles that they kind of put into them, kind of whip it and get some air bubbles inside. So this is made of sugar with a bunch of air bubbles inside. So those air bubbles are gases, and they can respond to changes to the peeps. So take a minute and watch the video of Pierre and Marie, the bunnies, marshmallow bunnies, named from Marie Curie and her husband Pierre. They both won Nobel Prizes for radiation. But see what happens when they go into a vacuum pump. So when the vacuum pump was turned on for the stunt bunny, the air was all sucked out of the container, and so there's less pressure. And so those gas particles within the marshmallow can start to expand. And the more air gets taken out, the more the bunny expands, the more those gas particles expand. Then when the professor turned the knob and the air pressure came crashing back in, it just squished the bunny, because now it's exerting so much more force back on that it's pushing all the gas particles together, and the bunny shrinks to a little bit less than its normal size, because as it expanded, it was really losing some of the gas. It was breaking some of the seals in the marshmallow. But what we found was, as pressure was increased on the bunny, the volume of the gas particles were squished smaller. So higher pressure pushing on, say, a balloon would squeeze it smaller, into a smaller space. So pressure is that outside air pressure pushing on the gas, and the volume is just the size of the container. The opposite was true when they originally took off the pressure on the bunnies. As they took off the pressure, the gas particles could expand, so the volume of those little gas particles, those little bubbles within the peeps, were increasing. So if you'll notice, volume and pressure are inversely proportional. When you increase one, you decrease the other one. If you double the pressure, you're going to cut in half the volume. And how do we measure that? In real life, when the hurricanes are coming in and they say the pressure is dropping, normally when storms come in, the storm is really just a lot of air and moisture. And so as it comes closer to where you are, it's pulling a lot of the air out into the storm. The storm is growing. So some of the air gets pulled out. So you're going to see a barometer drop. So the weatherman will say it's going to storm today, or there's a hurricane coming in, and we're seeing the pressure drop. And so that pressure, all that air gets pulled out into the storm. And as the storm comes crashing in, the pressure goes back up because that air all kind of moves back into the area. So we have to have a way of measuring pressure, air pressure. So this is an old barometer. These are the original ones. They were made with mercury, which we can't use anymore because it's highly toxic. But what they did was they had a tube and made a vacuum in it, took all the air out, turned it over, and put it down inside a container of mercury. So some of the mercury got drawn up into that vacuum. So what they would do is they would literally just measure from here to here. Air pressure is pushing down because that's exposed to the outside, that pool of mercury. And as the air pressure gets higher, it's going to push the mercury up higher into the tube, and that's your air pressure. What the distance is between the top and the bottom of that column. If the air pressure is higher, it's going to move this column up a little higher. It will have measure a higher pressure. And they literally just measured in millimeters from the top of this column to the top of the pool. Higher pressure would force that column up, and it would go up above that blue line. So the pressure, the units that we use for pressure is actually just millimeters of mercury. So it could, on news they measure it in inches, but generally in science we measure it in millimeters of mercury. Now we don't have to write the Hg, that's just what the old barometer has. You can do this with water, and now they really have digital barometers. There's a certain pressure that on a clear day, if you're standing at the beach, this is the pressure you're going to have of the air pushing down on top of you in terms of these millimeters of mercury, and it's 760. We call that standard pressure. It's a pressure that comes up a lot in gas laws. So we'll do some math with these gas laws. We said that anytime whatever volume does, pressure does the opposite. So if the pressure is going up, that's like the squeeze pushing in on the volume of the peeps. The volume of that size of the peep is going to drop. So there was a man named Boyle who worked with looking at pressure of gases versus volume, and this is his equation. V1P1 equals V2P2. The ones mean the starting conditions, like before the peeps went into the vacuum pump, what was their volume, what was the pressure on them. So if we worked a problem over here on the side, so let's say our volume was 20 mils. We had a balloon filled with 20 mils of some gas. And say the pressure we read off a barometer in the room was 725 millimeters. And then, so these are our initial values. These are our finals. The twos are the final values. After you change one of either the volume or the pressure, what happens to the other one? So what we're going to change is we're going to change the volume. It's no longer going to be 20 mils. We're going to change it to 25. We're going to allow the balloon to expand 5 mils bigger. So we want to figure out what happens to the pressure. So from V1 to V2, the volume is going up. So we said these variables are opposite each other. So in this particular problem, if volume is going up, our pressure ought to be dropping, because the only way for that gas to expand is if doesn't have as big a squeeze on the outside. So all we're going to do is plug these numbers on the right into that equation. So V1 is 20 mils. Volume of a gas is usually given in milliliters or liters. The pressure is 725 millimeters of pressure in that pressure unit that we use. The volume is expanding to 25 mils, and we want to know what the new pressure is. So P2 is what's the final pressure after you do all this work. So all we're going to do is multiply the left side and divide by the 25 mils. Or if you want to rearrange it, it would be 20 mils times 725 millimeters divided by 25 mils. All right, so we're just going to punch that in the calculator and see what we get. And you will see that your P2 comes out to be 580 millimeters. Because we said the only way for the volume to expand and grow was for the pressure on the outside to drop. So that does fit our prediction. So if you'll open the combined gas law problem sheet on Google Classroom, you'll see these problems. The first 4 problems are on Boyle's law. And so you notice we have some milliliter and some millimeter numbers given in this problem. So that's Boyle's law. What we're doing here is we're holding temperature constant, because temperature can impact the volume and the pressure on a gas also. So we're not changing the temperature at all. So V1, we're going to make our little list of variables that we were just doing. So V1 is the original volume, and that dot behind the 0 means it's significant. P1 is 720 millimeters. So that's the pressure on the outside of the balloon, say. This is our question: how many milliliters would the balloon occupy if we increase the pressure to 750? So from P1 to P2, we've increased our pressure. So we're squeezing more on the outside. Picture a balloon and picture squeezing on it. That ought to force it into a smaller volume, because V and P are always opposites each other. Higher pressure squeezes the particles closer together and the volume drops. So our volume ought to be something less than the 150 that we started with. So to plug in, we're going to use our Boyle's law equation, and we're going to plug in the numbers. So 150 milliliters times 720 millimeters equals V2 times the final pressure of 750 millimeters. So the V2 is like our X. To solve this, we're going to divide both sides by 750 so that it cancels out here on the right. Now, you don't have to show that if you don't need to. It's fine. So that leaves us with V2 equals, so multiply the top two numbers, divide by the 750, and your units, as far as units go, millimeters cancel out. And we said that at a higher pressure, 720 up to 750, the volume ought to drop something below 150. So see if you get something less than 150. And we do. We get 144 milliliters. So that is our final volume. On question 2, pressure can be given either millimeters or ATMs of pressure. And ATM stands for an atmosphere. So if you're standing there on the beach at sea level, it's 760 millimeters is normally on a clear day, that would be the pressure. If the other way we could give it is what's called atmospheres. 1 atmosphere is exactly the standard pressure. So standard pressure, if they just say to you, what's the volume at standard pressure, they just want you to know what that number is. Standard pressure is either 760 millimeters or 1 ATM. So the ATM just means atmospheres of pressure. So you could be given those in either two units. Notice in this problem, we're using atmospheres of pressure. So the starting volume here is 190 milliliters of pressure. That's how big the balloon is. The pressure from the outside pushing in is 1.05 ATMs. And we're looking for the volume when we get up to standard pressure. And so since we've used ATMs here, we want to use the standard ATM pressure. Okay. So you're going to solve here. Our pressure went down 1.05 to 1 ATM, so the pressure dropped. We would expect the volume to increase. So plug your numbers in, see what you get for V2, and see if it's something less than that original 190. And then we're just going to work problems 1 through 4 on that combined gas law sheet.